Now we're looking at applications that have to do with exponential growth or exponential decay. And so let's look at the following formula. So these are model populations that obey the law of inhibited growth. Many natural phenomena follow the law that an amount A varies with time t according to the following function. So A of t is equal to A sub 0 raised to the A sub 0 times E raised to the k times t power. We say that A sub 0, this is the original amount when the time is 0, t equals 0, and k cannot equal 0 and is a sum constant. If our constant k, that value in our exponent, is positive, then we can say that the amount of A is increasing over a time. If that value k is less than 0, we have a negative k value, then the amount A is decreasing over time. In either case, when an amount A varies over the time according to the equation, it's said that it's exponential law, or, and it looks like I cut off what that was saying. Okay. So an exponential law or exponential decay. Law of exponential decay is what I believe it was going to say. Notice that these formulas in the next couple of things is the exact same. So if we had an uninhibited growth of cells, so this model gives the number n of cells in a culture after time t has passed. In the early stages of the growth is n of t is equal to n sub 0 e to the kt. We're talking about a growth, so we talked about that k had to be positive. N sub 0 is the initial number of cells at time t equals 0. Again, k is positive constant that represents the growth rate of those cells. Okay, so let's look at an example using this. So we're given that the number n of bacteria present in a culture at time t in hours obeys the law of uninhibited growth. N of t equals 1000 e raised to the 0.01 t. So determine the number of bacteria when the time t was 0. Well, notice if you plug in 0 for t, or if you just remembered when I had said what was the initial amount, but if you didn't remember that, you could plug in 0 for t, and this would give us 1000, right? E raised to the 0.01, and t is 0. We'll recall a number other than 0 raised to the 0 power is 1. And so this is equal to 1000 times 1. So our initial amount of bacteria when time t, at the initial amount when t is 0, is equal to 1000. Okay, so that was part A. So part B, what is the growth rate of the bacteria? So K in our formula was equal to the growth rate. And so the growth rate, K, is equal to 0.01. This is in terms of hours. I needed to see what the time was. So the growth rate is increasing 1% per hour. So what's the population in 4 hours? So we just want to use our formula for n sub t, which we're given, and we're going to go in and we're going to plug in 4 wherever we see t. And so this is equal to 1,000 e raised to the 0.01 times 4 in that exponent. So we're taking 1,000 and multiplying it to e raised to the 0.04. And so doing that, after 4 hours, there's going to be 1,000 approximately. And I'm going to round because it's 0.8. I'm going to round up. So I have 1,041 bacteria. So population of the bacteria is 1,041 after 4 hours. When will the number of the bacteria reach 1,700? So we know what n sub t is. N sub t is 1,700. This is equal to our initial amount, 1,000, e raised to the 0.01 times t. So isolate your exponential piece. Let's divide both sides by 1,000. When we do that, we can reduce and we'll have 17 over 10 equals e raised to the 0.01 t. We want to take the natural log of both sides. We know the natural log of e is just equal to the exponent. This is saying e to what power gives you e raised to the 0.01 t. And so that would have to be 0.01 t. So to get t by itself, we can divide both sides by 0.01. So natural log of 17 divided by 10. And then take that and divide it by 0.01. And if you do that, we get t is approximately 53.06 hours. Okay. And I'm just looking at my answer just to think about, does that sound reasonable? And if it took 4 hours to go from 1,000 to 1,041, that's only 41 bacteria. We're going from 1,000 to 1,700. So that's like 600 more. So it seems kind of reasonable that I got 53 hours. And then the last question is, when will the number of bacteria double? Well, if we started with 1,000, when it doubles, that tells me that I'm going to have 2,000. I was a little confused because I had C up here, but that was D. E is population double, so that is 2,000 equals to our initial population of 1,000. E raised to the 0.01. And again, we're trying to find out what T is. So we can do that by dividing both sides by 1,000. 2,000 divided by 1,000 is 2 equals E raised to the 0.01 T. Again, we're going to use logs to help us to solve. So take the natural log of both sides of our equation. We get the natural log of 2 equals the natural log of E raised to the 0.01 T. Natural log of E is just its exponent because it's saying E raised to what would give us back this E raised to the 0.01 T. So it would be 0.01 T. So let's divide both sides by that 0.01. And so we get T is equal to the natural log of 2 all over 0.01. So plugging that in, natural log of 2 in your parentheses divided by 0.01 gives us 69.31 hours. 69.31 hours. Okay, so let's go to the next problem. So the following says, a culture of bacteria obeys the law of uninhibited growth. If N is the number of bacteria in the culture and T is the time and hours, express N as a function of T. Okay, so N is the number of bacteria in the culture, and T is the time in hours. And we want to express N as a function of T. When we have some initial amount, let's call it N sub 0, we have E raised to the rate that we're growing, which is K, to the T power. Okay, so part B, so that's part A. That's just the generic formula. And so now we're given information, so we can start figuring out what some of these variables are. So if 500 bacteria are present initially, and there are 800 after 1 hour, how many will be present in the culture after 5 hours? Okay, so this right here, this information, this first part of this question, this is going to give us enough information to figure out what K is. So we're given the initial amount that was present, which was 500. So right now we have N of T is equal to 500 E raised to the KT. But we're given another bit of information about the number of bacteria and the time. So if we plug that into this equation, we'd be only left with T. And so we're given that there are 800 bacteria. So we know there's 800 in there. This is equal to 500 E raised to the K times T. Well, there was 800 1 hour later. So our T in this case is 1. So let's solve for K. So let's divide both sides by 500. If we do so, those zeros cancel, leaving us with 8/5 equals E raised to the K power. So let's take the natural log of both sides. So the natural log of 8/5 equals the natural log of E to the K. So we know K is equal to the natural log of 8/5. We really don't want to round it until the end if possible. Let me see if a natural log of 8/5 gives us something. Well, natural log of 8/5 doesn't go on, that decimal doesn't go on like sometimes it does. K is going to equal 0.47. Okay, so we figured out what K is, and so now we have our formula that could represent anything now with this information given about this bacteria. So we know the initial amount was 500. This is E raised to the, our growth rate is 0.47 times T. So how many will be present after 5 hours? We can just go in there now and plug in 5 for T. So we have N of 5 equals 500 E raised to 0.47 times 5. Okay, so E raised to the 0.47 times 5. And that times 500. So that would give us 5,200, approximately 43 bacteria. Yeah, it's kind of good to kind of think about your answers and do they make sense? So let's just go back to that part B, that first part about that 47. That's saying that my growth rate is about 47%, and this is per hour. And it grew from 500 to 800. And so I know that 1,000 is going to be 50%. Okay. That makes sense. If I'm 5 hours and I'm 800, if I kind of almost double each time. Okay. Okay, so the next example or part says, how long will it take for 20,000 bacteria? And so part C, we know the amount, which is 20,000, is equal to our initial amount, 500, E raised to the 0.47 times T in the exponent. So let's divide both sides by 500. So 5 goes into 240 times. So I have 40 equals E raised to the 0.47 T. Take the natural log of both sides. Well, natural log of E, again, is just its exponent. So we have 0.47 T is equal to the natural log of 40. Divide both sides by that 0.47 to get T. So natural log of 40, close your parentheses, divided by 0.47. So that gives us approximately 7 hours, 7.85 hours. .85 hours doesn't really sound great, does it? So we could figure out how many minutes. So if I did 0.85 times, there's 60 minutes in an hour. That would give me 51 minutes. So this is equal to 7 hours and 50 minutes. actually 51 minutes. Okay, so that's how long it would take to grow from 500 to 20,000. Okay, so radioactive decay. Let's pull this up. Okay, so the amount of radioactive material present at time t is given by the following formula. A sub t is equal to a sub 0 e raised to the kt power. It's a decay rate, and so decay, remember, our k value is a constant and it would have to be negative, less than 0. So a sub 0 is the original amount of the radioactive material, and k is the negative number that represents the rate of the decay. So let's just read through the following. So all radioactive substance has a specific half-life, which is the time required for half of the radioactive substance to decay. Carbon dating uses the fact that all living organisms contain two kinds of carbon, carbon 12, a stable carbon, and carbon 14, a radioactive carbon with a half-life of 5,730 years. While an organism is living, the ratio of the carbon 12 to the carbon 14 is constant. But when the organism dies, the original amount of carbon 12 is present remains unchanged, whereas the amount of carbon 14 begins to decrease. This change in the amount of carbon 14 present relative to the amount of carbon 12 present makes it possible to calculate when an organism died. So notice this is just the same thing as that one original equation that we had, a sub t equals a sub 0 e raised to the kt power. So let's look at a radioactive decay problem. So it tells me that the half-life of radium is 1,690 years. If 10 grams is present now, how much will be present in 50 years? Okay, so we want to figure out what that growth decay or decay rate, not growth, decay rate is. So we know what the initial amount is, right? We know that the initial amount was 10 grams. So let's put 10 grams in here. So this is E, right, raised to the KT. But they've given us a little bit of information. They told me that half-life of this radium is 1,690 years. So half of the original amount, which was 10, that would be 5. So I know that my amount of this radium left would be 5 is equal to 10 e to the k times time. Well, that was going to take me 1,690 years to go from 10 grams to 5 grams. And so with that information now, I can figure out what my K value is. So let's divide both sides by 10 and we get 1/2 equals e to the 1,690K. Take the natural log of both sides. So natural log of 1/2 equals the natural log of e raised to that 1,690K power, which is just our exponent. So I'm just going to write that for now. divide both sides by 1,690. And that's what we're going to get is our K value. So let me see if that gives me a reasonable decimal. So I have the natural log of 1/2, and then I'm going to divide that number by 1,690. It didn't like mine at all. It's rounding weird. So let me pause while I fix my key. Let's leave it like this. Right now it's telling my calculator is telling me it's 0. So that means it's rounding pretty far. So let me just see. So I'm going to leave my K value as this natural log of, I'm going to write it as 0.5, 0.5 all over 1,690. And so I have my formula, A sub t is equal to 10 e raised to this natural log of 0.5 all over 1,690 times t. We want to know how much is present after 50 years. So we're going to plug in 50 for t. Okay, so again, it's like a calculator exercise. So I'm going to take 10 parentheses, my e value. The exponent, I'm going to have parentheses, a couple parentheses, natural log of 0.5. I'm going to multiply that by 50. And I'm going to divide that result by 1,690. And that's all in the exponent. And if I do that, I get this is equal to 9.8 grams. Okay, so after 50 years, the organism that died, that originally had 10 grams, is now 9.8 grams. Okay, so we're trying to estimate the age of a tree. So a piece of charcoal is found to contain 30% of carbon-14 that it originally had. When did the tree die from which the charcoal came? Use 5,730 years as the half-life of carbon-14. Okay, so we need to see again what our rate is for K, our decay rate. So we have some original amount. I don't know, let's say A equals the original amount of carbon-14. Present when the tree died. Okay, so we know that half of that amount will still be there. So A over 2 is equal to the original amount A, E raised to the K, but it's going to take me that time 5,730. So if we get E by itself and we divide both sides by A, I'm going to think of it actually as multiplying both sides by the reciprocal, so I don't have to deal with the complex fraction. So let's multiply both sides by 1 over A. So notice that that 1 over A times A over 2, the A's cancel, and we're just left with 1/2 is equal to E raised to the 5,730K. So let's take the natural log of both sides of our equation. And so we have the natural log of 1/2 equals the natural log of E, but natural log of some E is just its exponent. So 5,730. Okay. So I know K is equal to the natural log of 1/2. I'm going to write it as 0.5 all over 5,730. Okay, so we know what K is. And when we found this piece, it had 30% of the carbon 14 that it originally had. Okay, so A was the original amount. So if it contains 30%, so 0.3% of the original amount A is equal to our original amount A, E raised to K, which we're going to write as this ln of 0.5 all divided by 5,730 T. Well, if you divide both sides by A, notice A's cancel, and you're just left with 0.3 on that one side is equal to E raised to this natural log of 0.5, that divided by 5,730 times T. Take the natural log of both sides of our equation, we get the natural log of 0.3. Natural log of E is just its exponent. So if I multiply by that reciprocal of what's in front of T, I would get that T is equal to the natural log of 0.3 times the reciprocal of this. So that would be 5,730 over the natural log of 0.5. Okay, so the natural log of 0.3 times 5,730, take that result and divide it by natural log of 0.5. And if we do this, this is approximately 9,000, that piece of charcoal, 953 years old. So there were a couple of other formulas given in this section. And I'm okay with you just looking at what those formulas are and just using them. If I was to give you a test on them, I would give you the formulas. So let me just give you the formulas real quick. You don't have a chance. I don't think we have time to go through one unless you want to stay after class, and I can do that. Hold on, let me pull up the formula real quick. And we have Newton's law of cooling. So Newton's law of cooling says the temperature U of a heated object at a given time t can be modeled by the following function. So our temperature, which is U of t, is equal to capital T plus parentheses U sub 0 minus t in parentheses times e raised to the kt, where k is less than 0. Again, that constant k being less than 0 makes sense because our temperature is going down, it's cooling, so it has to be negative. Where T is the constant temperature of the surrounding medium, U sub 0 is the initial temperature of the heated object, and K is that negative constant. So I think we might have time to do one of these. Okay, so in this problem, we're given that a thermometer is reading. So a thermometer is reading 72 degrees Fahrenheit, is placed in the refrigerator where the temperature is a constant 38 degrees Fahrenheit. Okay, so if the thermometer reads 60 degrees Fahrenheit after 2 minutes, what will it be reading after 5 minutes? How long will it take before the thermometer reads 39 degrees? Determine the line, determine the time that must elapse before the thermometer reads 45 degrees. What do you notice about the temperature as time passes? Okay, so our original temperature was 72 degrees. Where T is the constant temperature of the surrounding medium, U sub 0 is the initial temperature. So our initial temperature is 72 degrees. Our capital T is 38 degrees. Capital T is the constant temperature, and we're putting it in the fridge at a constant temperature of 38 degrees. So far we have the formula U sub t is equal to capital T, which is 38 degrees, plus U sub 0, which is 72 degrees, minus T, again, which is 38 degrees, all times e raised to the k times t. We need to figure out what k is, and we can figure out k because it says that the thermometer reading after 2 minutes is 60 degrees. So we know when t is 2, this is equal to 60. So let's go into our formula. 60 equals 38 plus 72 minus 38. That is 34. E raised to the kt. So let's isolate this. Let's subtract 38 on both sides. So that's 22 equals 34 e raised to the kt. Divide both sides by 34 to get e by itself. And so we have, and that reduces, 2 goes into both of those. So 11 over 17 equals e to the kt, take the natural log of both sides. Natural log of e is just its exponent. So kt, but we know what t is, right? That t over here was 2. So it's 2 minutes. So let's divide both sides by 2, and we can have what k is. So natural log of 11 divided by 17, all divided by 2. So this gives us negative 0.22. Because we're out of time, I'm going to stop there, but you basically now have your formula that we could answer any of those questions, and we can make our formula a little neater. So we have our u sub t is equal to that 38. Plus 34 e raised to the negative 0.22 t. Okay, so if I gave you a question with Newton's law of cooling again on the exam, I would give you that formula and you would need to know how to apply it.